Okay. Shut up! Don't forget, Ninja Bible Study today, noon to 1. Free lunch, God and Grub. Take it down to go to the cafeteria, sign in, take it down to the terrace room. A bunch of us go and have lunch in the caf right after class. So if you want to sit and eat lunch in the cafeteria and then just walk down to the terrace room without a tray, you can do that with us as well. But it's only for ninjas. So if you're not a ninja, then tell them you're a ninja. Make weight.
Gotta make weight.
Gotta make weight. Gotta make.
Yeah, this whole story.
Get your weight class. If there's too many in your weight class, you can't go.
All right, so we're gonna call this object-oriented stuff, based on. Oh, we're not. I thought I clicked it. Ninja. Pass the test. All right, so. Based on some of the questions I was getting on the homework, there's something I want to review from last semester, just to kind of bring it back into focus for us this semester, is this object-oriented stuff. We talked about this last class, and I think the class before that too. What goes into so a class has 3 members. There are 3 things that classes are collections of. One is a collection of fields. These are variables, pieces of information remembered by the class, remembered by instances of the class. Constructors. So these guys they look kind of like methods. We talked about this last class when we were talking about the new keyword and how we have that syntactic sugar thing, where in Java they've actually taken away the return type for constructors because they always return a memory address. And they're always used in conjunction with the new keyword. So constructors look a lot like a normal plain Jane method, but they always have the same name as the class, and they never return a value. They never have a return type. They never actually have a return statement inside there either, but I think I showed you last time in Objective-C how there's some magical stuff that's in there that we don't actually see. Remember in Objective-C, the very first line was self is equal to something. Then we did a bunch of stuff that made it unique to that object in the constructor. And then in the end, we finally returned self, which is a pointer to that particular object. So older languages made you actually go through the process of defining the value of self, or in our case in Java, defining the value of this, then clarifying the difference between generic plain Jane object and whatever you're building. In our last assignment, we were building a fraction, and then ultimately spitting out the value of this or self as the returned value from the constructor. Java said, well, you're always returning a memory address, so we're not going to make you tell us that, and we're also not going to make you do it. Not going to make you actually return it. We'll just do it for you. So constructors in Java have a little bit of syntactic sugar associated with them, so we differentiate them by always having them match the name of the class. So they look a lot like a method, but their name is always the same as the name of the class, capitalization and everything, and they will not have a return type, and they will not have a return statement inside. Then we have normal methods. Normal methods, these are the functional abilities that an object can do. So fields allow us to remember pieces of information. So allows us to associate name-value pairs with an instance of an object. So for like a fraction, we can remember the fraction's numerator. We can remember the fraction's denominator. Those would be examples of fields. Methods, for example, for today, we were supposed to write a method called add, which takes another fraction as a parameter and adds that fraction to the fraction that was passed to it. Adds the fraction associated with this dot numerator and this dot denominator to the fraction that was passed in, ultimately building a new fraction and returning the result. All right, so that's the overview there. If we kind of summarize it here, fields allow us to remember pieces of information related to an object. These are our variables. Constructors allow us to build instances of an object. Note, we can have multiple constructors as we might want to build objects with different, I'm just going to say, materials, different inputs. So for instance, in our fraction class, we've built a fraction. We have a constructor that takes two integers, a numerator and a denominator, and builds a fraction given those two pieces of information. We also have a second constructor that takes a string. That was the last homework assignment. And that guy, we had to break apart that string and extract the numerator and extract the denominator, setting our two fields equal to those. Both of those constructors will result in a built fraction, in a fraction that has a numerator and a denominator. But we hired two different people. We have one guy that we give him two numbers, he builds a fraction. We have another guy that if we give him a string that's in a specific format, he'll build us a fraction. That makes sense? So both of them ultimately build fraction objects. They just might have different materials or different inputs to ultimately build that object. And there's no limit, well, there technically probably is a actual limit for the number of constructors you can have, but it's probably something like the size of int or something. You probably can have 2 billion constructors if that just in your world made sense or something like that. Okay, but generally speaking, you can have as many constructors as you want. But you cannot have more than one constructor that takes the same type or number of parameters. That is to say, you can't have one constructor that takes an int A and another constructor that takes an int B. From Java's perspective, those are the same constructor. They both take an int. Java doesn't care what you named your parameters. Make sense? All right, so in our case right now, we have two unique constructors, one that takes two integers and one that takes one string. Questions?
So if we had a constructor that took one integer and then another constructor that took two integers, that would be okay.
That's okay. Yeah, different number and or type of parameters, yeah. So you could have a constructor that takes one integer, you could have a constructor that takes one string, that's allowed.
Okay.
You just can't have two constructors that take one integer. Yeah, they have to be uniquely identifiable. Yeah, this isn't some kind of weird rule. Just if you look at your constructors and you just remove the variable names, you should be able to tell them apart from each other. Okay, by the types that are being passed in. Go ahead.
So, what exactly would a constructor look like in Java code?
So we go back here to this guy. Where's my Eclipse? There we go. Don't want to do that yet. We're building a processor there in Java. Here's one constructor right here. Its name matches the class name. It has no return type. This guy takes in two integers. Here's a second constructor that we just referenced. This guy takes a string as a parameter. So we have two separate constructors here in the fraction class that we wrote. One that takes two integers and one that takes a string. The name for a constructor must always match the name of the class, and it will never have a return type, and it will never return a value by our doing. Yeah.
So, how does it run if we don't have a way of distinguishing it from the main?
Ask that again.
How exactly do we run that version of that constructor?
Okay.
When it doesn't
Yeah, so here's examples right here. So here's us over in this case, inside of fraction.java, this is where we are defining those constructors. They're unused resources at this point. We're just defining what they are and what parameters they take. Over here in driver, for example, I am building 4 fractions right here. The first 3, I'm using that constructor that takes 2 integers. The next one, I'm using that second constructor that takes a string. And notice that constructors always are preceded by the new keyword, that's our real estate agent that always boils down to a memory address. That's why a constructor doesn't have a return type in Java, because its return type would always be a memory address. And that's why a constructor doesn't actually return a value inside of it, because Java takes care of that for us as well. All right, so this is us. So these 3 lines right here, new fraction int int, new fraction int int, new fraction int int. These guys are calling this constructor right here, our fraction constructor that takes 2 integers. This last one, we are building a fraction with a different set of materials. We're passing this constructor a string, and so that's going to call the version of the fraction constructor here that takes a string as a parameter. Does that make sense? Mm-hmm. All right, good.
For the homework, I wrote a fraction constructor that took in 2 fraction objects.
Yeah, you're not alone.
Is that okay?
No.
No?
I'm going to explain it today. That's why I'm taking a little bit of time here to go over some things for some clarification. It's not horrible. It just doesn't necessarily make a whole lot of sense for you to say, I guess there's a world where it could make sense, where you say, okay, I want to build a fraction in terms of 2 other fractions, and I want my new fraction to be those 2 fractions added together. In a weird universe, that could make sense, right? Because that does fit. I mean, that doesn't break the rules of what I'm saying here. We can have multiple constructors, as we might want to build objects with different materials. Who's to say that you don't want to build a fraction by somebody else handing you 2 fractions, just say, look, bud, just add these together and give me a new fraction. Kind of a very special purpose constructor, but could be okay, let's say. But it wasn't the intention. The intention was to write a method. So we're going to say methods, our third type of thing. These guys allow us to give instances. For right now, I'm just going to keep using the word instances because we're going to differentiate static versus non-static. But for right now, let me just say instances, which I could have. Here, just going back to this real quick. We have 4 instances of fraction here. F1, F2, F3, and F4. All of these guys are fractions, but they are unique fractions. F1 is the fraction 1/2. F2 is the fraction 1/4. F3 is the fraction 3/16. And F4, through a little bit of manipulation, will ultimately end up being the fraction 3/18. Okay? These are 4 unique fractions from each other. We would call those instances of fractions. That make sense? So whenever I use that term instances, I'm talking about multiple versions of the same type. All right, so all of us, many of us in here have a smartphone. We each have an instance of a smartphone. We'll just assume we all have the same kind and they were built from the same unique blueprint, right? But we all have an instance of a smartphone. So if I throw mine against the wall and crack the screen, it doesn't have an impact on any of your phones, right? Because I only broke this instance. All right. So methods allow us to give instances abilities beyond just holding values after they have been created. For example, for today's homework, we were to add an additional ability to the fraction class called add. And that ability knows how to add a fraction to another fraction. Does that make sense? So to kind of follow through with this, let's go ahead and write that. All right. So the intention for the homework was to come in here to fraction. And we're going to just, actually, I'm going to put it near the top. I'm going to compress these. I don't know if you noticed that, but you can kind of minimize your functions in here to make things a little bit easier to see. I think we could do the same thing in Atom last semester. All right, so I'm just going to go right after our two constructors. So these are our two constructors, and then I'm going to say now we have our methods. Java does not care the order in which we put these things. We can have fields and methods and constructors just strewn all about the place as long as they are between the opening curly brace for the class and the closing curly brace from the class. If we think of that class as kind of like a bag, our fields, constructors, and methods must go inside the bag. Okay? And they can't be defined inside of each other. You can't put a constructor inside of another constructor. You can't put a method inside of a constructor. So these guys have to exist as individual little pods inside of our bag that is the class. Does that make sense? Common mistake for inexperienced programmers is for them to start, especially with curly braces now. Because one of the reasons we used Python initially is it forced that indentation. And one of the things that starts happening once you get into languages that require curly braces is you start seeing yourselves move away from organized code because you're starting to do a lot of copying and pasting and things like that. So really try to make an effort to have an opening curly brace, a corresponding curly brace with your stuff indented inside of it, and then you're kind of reinforcing that pattern that you should have got it started at least with the Python stuff, right? Okay, so when you're done with your program, if you don't see indentation like this, try to practice doing that. It's not just for your health. You know, well, actually, it is for your health. It's for your sanity, right? It's not just to make me happy. I'll be able to read the code regardless. It will make your code easier for you to debug when you have weird stuff going on. All right? So, typical convention says that a class has all the fields at the top, followed by the constructors, followed by your methods. That is the common cadence for objects. Java doesn't care. Just toss them in there wherever you want. You can even rotate. You can have fields and a couple of constructors, toss them a couple more fields in there. It doesn't matter. That'll just be really hard for a human being to follow, but Java's cool with it. Java's cool if you put your whole thing on one line. It just does not care.
Don't they have competitions?
Yeah, I mentioned, yeah, there's I don't know when the last time they had it, but they used to have competitions for that stuff.
We should do a hackathon instead.
Well, it's interesting, but it's not that instructive. Well, let me, just because it's on my mind right now, let me, I think you guys saw, actually it probably came from my email, didn't it? The survey thing, right? All right, so and we're still processing through the results, but I wanted to give a little bit of explanation for some of my classes why you might feel that my homework assignments take longer than your other classes. First of all, programming is harder. Well, harder that's the wrong term. If you go back to the very first class, I mentioned programming is like a sport, and you just have to put in the reps, and there's nothing I can do to take away the time it's going to take to do the reps. Having said that, and I actually really, really, really recommend this book. It's fascinating. There's this book called Outliers. I forgot that if you just Google it, you can come up with the author of it. But this book talks about, it's just fascinating things that we think we know that we really don't. So I'll just give you a quick, go ahead.
Malcolm Gladwell.
Malcolm Gladwell? Gladwell. Okay, that sounds right. So here's an example. I'll give you kind of a stupid example first, and then I'll give you an example that's a little bit more connected to what I'm talking about here. So we've all heard of the NHL, professional hockey, right? Okay. So kind of an interesting thing about professional hockey is they have a higher percentage of Canadians in the in professional hockey than any other country. Kind of makes sense. Hockey is a really, really popular sport in Canada, so that would make some sense, right? That's not what this is about. But now, if you take all of the Canadian NHL players, a shocking percentage of them have birthdays in January, February, or March. Why? Is it that January, February, and March people are just naturally more talented at hockey? That doesn't seem right, does it? We got a theory?
Because by the time they're born and when their birthday comes up, it's getting to like winter time, which is when hockey's big. So they almost get an extra year of practice over everybody else.
Okay, you're actually not horrifically off.
Just slightly off.
You're slightly off.
No, that would make sense.
Okay.
Would it be like 9 months after the Stanley Cup? Or
I've heard somebody else say that too. Nope. No. I mean, at that point, you can kind of make the argument that, maybe the parents were celebrating the Stanley Cup, and so they must be a big hockey family, and there could be some truth to that, but it actually, at least the strong evidence indicates, it's when the age cutoff is for junior hockey. Would be in 10 years and younger, the difference between an 8-year-old and a 9-year-old is substantial in terms of their, how fumbly they are and stuff like that, their coordination, things like that. So if you're one of the older kids in junior hockey, you have a substantially better chance of making the all-star team, which gets you into the traveling league, which gets you better coaching, and then that snowballs over time, right? So they're getting more time on the ice. They're getting better quality coaching, more individual instruction, all this stuff. So they end up getting these opportunities that the younger kids maybe didn't get. And it's because of the cutoff for when you're in the next level up. Whether am I the youngest kid in the next level up, or am I the oldest kid in the current level? The oldest kids have the advantage up to age 10-ish, let's say, because they are the ones that tend to get more ice time because they're more coordinated. They tend to make the all-star team. They tend to be on the traveling squad, all these other things. So something as simple as the age break-off for junior hockey translates into NHL players. Isn't that fascinating? Okay, so now let's connect it a little bit closer to maybe our world. So most of us have probably heard the stereotype or something like that, that Chinese students tend to be better at math. We heard that? Okay. Do you think that's really true? Do you think the Chinese students are just flat out smarter than the American students? Is that just it? Do you think that's really true? Or can any human be just as smart as any other human? So here's an interesting, so let's say that I gave you 7 numbers and I told you, okay, you got 30 seconds to memorize these numbers. We won't actually do it, we won't waste the time doing it, but I say, okay, 13, 27, 8, blah, blah, blah. 7 total numbers, and you have 30 seconds to memorize them. Okay, about 30% of you, roughly, would be able to memorize those in 30 seconds. Almost 100% of Chinese folks would be able to memorize those numbers in the same amount of time. Why? They're smarter?
No, they draw memorization from younger age.
No.
Wait, what? That's my answer.
Go ahead.
Their language is built.
Oh,
to
right.
memorize numbers.
No, close. It has to do with their language. The human brain's on about a 2-second loop. And the English language doesn't allow us to express 7 numbers within 2 seconds. The Chinese language does. So they can express 7 numbers in under 2 seconds, which then allows them to keep that in one cycle of their brain as they go through. It's because of their language. Nothing to do with where they're from, Now, having said that, that culture does put a greater importance on education. So that's where I'm swinging in here. So we've heard this law of 10,000, that become a master at anything with 10,000 hours of practice. It's kind of the thing. If you want to become completely competent in any one thing, you spend 10,000 hours doing it, and that will give you, that's just this rough number they've come up with for what differentiates a professional basketball player from a very good basketball player, something like that. Or a great programmer from a mediocre programmer, let's say. So it takes all of these hours of reps outside of school, outside of when you're forced to think about the subjects. And if you look at the education system in China, their school goes almost year-round, and their I'm sure the kids don't like it any better than the kids here would like it. Okay, especially when they're younger, then it just becomes part of, like, this is just normal, right? Okay, but they're spending more time in school. The general consensus would be that one of the problems with learning in the United States is summer break. During summer break, students stop studying. They stop reading. They're spending a lot more time watching TV. They might get a whole lot better at baseball, or a whole lot better at whatever sport they like, because that's when they grow in that field, but they're not doing those academic things during that time. So the short punchline of this is the more time you spend doing something, the better you will get at it, is the punchline. Now, you do need to make sure that the time you're spending is instructive time. If something is just beyond you, like if I gave you a homework assignment that just dealt with, like, invent time travel for Friday, right? Okay, you're probably not going to make giant leaps, even if you spend every waking moment between now and Friday. You're not going to make giant leaps towards solving the time travel problem. Okay? Maybe you'll learn a little bit or something, but that's not really an instructive type thing, right? But to have homework be something that's within your grasp, but you can't just sit down and pump out in 2 seconds, means that you're working towards those 10,000 hours, and a lot of instruction takes place. Now, not a whole lot I can do about, making this class take less of your time than some of your other classes. Maybe I'd argue that your other classes should make you take more time too. You're paying a lot of money for college, might as well get your money's worth. I never understood why students don't all take 18 credits either. Everybody likes the deal. Whether whatever it is, 20 grand a year or something, you get 12 credits or you get 18 credits in a semester. Same price. Take 18. It's like, well, my sanity. Wow, be sane later. No, that's only a half joke. Some people legitimately can't take that many individual classes, so then I'd make the argument to spend more time in the classes you are taking. Even going above and beyond what you're learning in the classroom, especially for things that you're interested in. Something like that. But in any case, there is a rationale to the reason, it doesn't do me any good to come in here, do all the work for you, then just say, okay, go ahead and find my one bug. And that's your homework for next class. And some of you find it in 2 seconds, tell everybody about it in Slack, and you've got no practice in. Okay? So basically, your life should be hell outside of the classroom because you're paying good money for that. That's the punchline.
Paying good money for hell.
That's amazing.
Because later on, you'll now be closer and closer and closer to those 10,000 hours. And do the math, what it takes to get to 10,000 hours of something to really differentiate yourself from being the Joe average to the, expert, professional, whatever, however you want to quantify it. But that's a lot of hours. So if you start getting into the habit now, that'll be better. And those video games can wait. The extra sleep can wait. You need a minimum amount of sleep, but you don't need to sleep in for 12 hours. Whatever. Okay. So questions about any of that? I highly recommend that book. It's fascinating. Absolutely fascinating. And it talks about all sorts of things, like plane crashes.
I hate planes.
What?
Okay. Years ago, you were something like I think 40 or 50 times more likely to be in an airplane crash. Today, that crashes never happen, and it's partly because of this. You were like 40 or 50 times more likely to be in an airplane crash if you flew Korean Air than if you flew any other airline. So then you might say, well, why? Was it because their pilots were worse pilots? No. It was a cultural difference. A co-pilot in the Korean culture, a co-pilot was, I'm kind of fast forwarding here just to get through this part pretty quickly. The co-pilot is less likely to question the captain in that culture. So when the co-pilot sees something that is off, they'll hint around and things like that rather than actually bring it to their attention. Where in many other cultures, people are just belligerent to other people. It's like, look, stupid. Engine number 2 is iced. We need to land. I mean, but it's fascinating to think that it's little cultural nuances like that. That's just respect to one's either elders or more experience or whatever, which kind of makes sense maybe in like normal situations. You know, like in the Korean culture, the more socially powerful person gets to sit down first. Everybody else will wait. That's not a deal breaker. Planes aren't crashing because of that, right? But you're in the cockpit of a plane, and especially if you're one of the people not in the cockpit, you want the co-pilot to speak up, right? And it's fascinating. They have a whole flight recorder of an airline that did crash, and they listened for like a half hour leading up to this crash of all these things that went wrong. All because the other people in the cockpit were hinting around to the pilot about what was actually wrong. It was so obvious to so many people. The pilot was exhausted, he had been flying for too long, and just wasn't processing the stuff, and nobody actually brought it up until they hit the side of the mountain. You know, and since then, you know, they've done the whole study on this thing. They've gotten, Korean Airlines gotten an award for like their safety record. Now it's one of the best in the world. It might even be the best in the world, because now they're paying super close attention to that, where other airlines just kind of were able to ride their cultures. You know, an American co-pilot will scream at the captain, no problem. That's the way it is. Just kind of fascinating stuff in the book that kind of makes you start thinking about all sorts of things that we thought we knew. Yeah.
They talk about Korean flight 801.
I don't know.
This was in 1997.
Sounds like the right year that the book was talking about, but I don't remember the flight number.
Malaysia flight that never showed up or whatever. They still can't fly.
I knew.
You know, that doesn't mean accidents still can't happen, but so many accidents are avoidable after the fact. That's why they do a whole study to try to find out, well, why did this happen? What were the series of events that had to occur? And the reality is that, like, I think the book talks about something like, I think 7 unique things have to go wrong in a row, typically for an airline to actually crash. I think if 6 bad things happen, you'd still be fine. And today, the planes basically fly themselves. I think your pilots can all lose consciousness, and
Unless it's the Boeing plane, then.
who knows? Who knows? But yeah.
Can't fly. It's like one of my biggest fears. I can't fly. It was ever since I was little, because there was like this flight that I wanted, and like it was so shaky. Like the plane was like going everywhere. Like the pilot was like, "Everybody, please, like put these masks on." I was like, yeah, it was donezo for me. Like there was no way.
Well, I've flown many, many, many times, and I'm still kicking.
You ever had to put that little mask thing on?
I did. I've had a double engine failure on a propeller plane when I was a kid.
Still fly? Like,
I didn't like flying for a while back then. I was a kid, but I've had an aborted takeoff.
What is that? Like,
that means you're like, it was coming out of Atlanta. We were getting ready to take off. I mean, the wheels had to be off the ground, or if not off, just about off. And all of a sudden, you just feel them power down in the front, go it's just bouncing. They pull off into the grass. You know, this is on a big three seats each row, so 6 seats across plane. Pilot comes over and says, yeah, we had an indicator light go off. We're going to check it. And he's just sitting in the grass while other planes are taking off by us. And then he's like, we're gonna try this again.
Wait, try this again?
Yeah, we didn't go back to the hangar or anything. So he pulls back in line. And we're like at the exact same point in takeoff. And all of a sudden, and this has to be like in the book of like things not to say. I think it was one of the flight attendants came over the speakers like, cell phones off, like really panicky, like screaming cell phones off, because I guess that must have been some indicator light that was like radio interference or something like that. And then we just took off and the rest of the flight was fine.
She's probably worried she's gonna die. She doesn't care what on you guys.
We were on a flight in, it was in Phoenix, Arizona, and it was really foggy, and it seemed like we were like descending forever, like coming in for landing. And then finally we got underneath the fog and we were like on top of houses. We were nowhere near the airport.
Oh my god.
And then you just feel them crank the engines, and we felt like he went straight up. And then the pilot just comes over, it's like, oh, we're gonna give that another shot.
We're pretend it never happened. Please, don't think that of you, please.
Always tells me like there's so much more likely for you to get in the car crash.
It's
so
so much more likely.
It's just
No, I get it. It's one of those irrational fears. Yeah, it's logic doesn't support it, but you feel the way you feel. It's just the way it is. All right, let's get back on track. So this is why you have hard homework, and you spend your time on your homework. And if your homework feels too easy for you because of this stuff, you've had it before, challenge yourself and give yourself more time. Make it harder. Do more stuff. All right? So for this assignment, we were to write a method. Not a constructor, not a field, but a method that returns a fraction, is called add, takes a fraction as a parameter. And this guy adds f to this, I'll put it in, to this fraction, and returns a new fraction object that is the sum of the two. That's what this function will do. So it's a function which has a return type, which takes 0 or more parameters. So if I am an instance of fraction and I'm being asked to add myself to another fraction, what I need to work, what I need in order to do my job is I need you to hand me that other fraction. That's this guy right here. Here's us inputting a fraction so that I can add it to myself, producing a new fraction that is the answer. That make sense? All right, so we're going to create an int denom. So we need a common denominator first, and the common denominator is going to be what? How do we come up with a common denominator? Multiply our two denominators together? Might not be a reduced common denominator, but it's a common denominator. So we would say my denominator times f's denominator. I will multiply the denominator that belongs to this fraction by the denominator that belongs to the fraction that was passed in. Storing the result inside of a local variable here called denom that will be my new denominator. Do you have a question in the back?
Yeah, when I was working with this function, it would always say that it would always come up with an error.
I have to see the code in order to tell you why. There's certainly a reason for it. Maybe you were outside of the curly braces or something like that. But this isn't a function. This is a local variable that is a pointer. It's how an object refers to itself from within itself. It's equivalent to the self variable from last semester. All right. So the result of this line is I will have a new variable, a local variable called denom that is equal to my denominator times the denominator of the fraction that was passed in. Everybody get what that line does? Int num is equal to, this is where we do our cross multiplication. So this is going to be this dot denominator times f dot numerator plus f dot denominator times this dot numerator. And we can kick that down the line if we want.
This is using the fractions that are on the front.
Yeah. This is if I pretend like I am the fraction, I am the instance of fraction whose add method was called. I am taking my denominator, I am multiplying it by the guy that was passed in, f's numerator. I'm adding that to f's denominator times my numerator, giving me my new numerator, which is going to be the sum of those two fractions when taking the common denominator into consideration. All right, and then we could actually return this directly, but I'm going to add an extra line here just so we see it. So I'm going to say fraction answer is equal to a new fraction, num denom, then return answer.
That's it.
How do you add fractions together? You get a common denominator,
Right.
then you create the summed numerator that takes the common denominator into consideration. And I'm supposed to return a new fraction here that is the sum of myself, the fraction represented by this, and the fraction that was passed in. How do I build fractions? I build them using constructors. I happen to have two integers to work with here. So I will call the version of the fraction constructor that takes two ints. He will build a fraction for me. I will store that in a variable here of type fraction. And then ultimately I will return that variable because I've advertised that the add function here returns a fraction.
So wait, so this dot denominator goes back to the other on the other page, like the
Nope.
no.
This dot denominator is me. That's
Oh.
my denominator. If I'm the version of fraction, if you said, Mike, add yourself to Chancery 1. Make weight. Okay, you say add yourself to Noah. In that case, you are asking me, Mike, to call my add method. So while we're inside of this add method, the way I talk about myself is by saying this. I am taking my numerator and I'm adding it to, now you had to hand me Noah. All right, so it's a good thing he's lost some weight for this competition thing. So you had to hand me him as an input. This is Noah here and as that input, right? Okay, so you've handed him and said, add yourself to him, but return a new fraction. So we're not going to modify, I'm not going to modify myself. I'm not going to modify him. I'm just going to use my two values and I'm going to use his two values and we're going to create a brand new fraction. Okay? So I'm going to say, I'm going to take my denominator and I'm going to multiply it by Noah's denominator. That's going to give me the new denominator for my brand new fraction. Then I'm going to take my denominator, I'm going to multiply it by Noah's numerator, I'm going to add that to Noah's denominator multiplied by my numerator. That's going to give me a brand new numerator that I'll be able to use to build the new fraction. Then I'll build a brand new fraction here using my numerator and my denominator, store that fraction inside of answer, and then ultimately return that new fraction. Make sense? So that's the ability now we've built into the fraction class. So out here, we'll stick with our example from a second ago. So we have two fractions, 1/2 and 1/4, and we've said Mike dot add Noah. So we're calling Mike's add function, passing as a parameter Noah. So inside of that add fraction, in here, this references Mike. F references Noah.
Wait, go back to it. Here, go back to it.
So it's making like that.
So in this particular example, this is Mike. F is Noah. In this exact example, all right, because inside here, I'm writing a generic function that knows how to add this fraction to another fraction. I happen to be showing you an example where the two fractions are specifically Mike and Noah. I am calling the add function that belongs to Mike. That makes sense? I could have just as easily said Noah and Mike. Now I'm calling Noah's add function. So inside of that one, this would be Noah and F would be Mike, the parameter that was passed in. Make sense? So now in the end, I should be able to say answer.display. And there's our 6/8. Those two fractions added together. All right, so that is the homework assignment. Write a function, not a constructor, not a field, a function that takes a fraction as a parameter and adds this particular fraction. The calling fraction is what we would usually say. So in this case out here, the calling object in this case is Mike. Mike is calling his add method and passing as a parameter Noah, which is another fraction. So in this case, we would say Mike is the calling object. He is calling his add method. Make sense? And clarify some stuff for people?
Yeah.
All right. This is a critical concept. Okay? And it's a concept we teach in 200. So it's either been forgotten or wasn't clear in 200. But that would have been the best time to learn it. The second best time to learn it is right now.
Yes.
So between the two. So stew on this. And if there's something about this that doesn't make sense to you, message me, whatever, I'll explain it again. But this is absolutely critical when it comes to object-oriented programming, to understand the concept that we talked about today. It is the bread and butter of object-oriented programming. All right, make sense? All right, so now what I'm going to do is just to make things kind of scary for us, so I can show a point. I mentioned it last class. I'm going to change my numerator and my denominator both to longs, which are just big integers, right? So if remember when we talk about the primitive types, right, we have a byte, a short, an int, a long. So an int is a 32-bit signed, so it's roughly negative 2.1 billion to positive 2.1 billion. Well, now I'm going to store it's a 2 to the 63rd, plus or minus 2 to the 63rd. So 2 to the 63rd power, it's that number, plus or minus that number. It's like 9.2 quintillion or something like that.
Yeah.
Big number. Okay. I'm only going to do this because I want to create a really, really, really big numerator and a really, really, really big denominator, and then we're going to try to reduce it. And we're going to see that that takes a long time. All right, so this just allows me to really force a huge number. Okay? So, long numerator, long denominator. We'll go ahead and have our constructor take in the two longs like that. in our add, we'll have our denom and numerator taken along. We should be fine. Should be fine there. Right. So all we've changed here is we now have the capability of holding bigger numerators and denominators. Still works for small numbers too. Just we inefficiently are storing them. We're giving ourselves 64 bits to store the number 6. We don't need 64 bits to store a 6. But who cares? We got plenty of memory. No, no big deal. All right, so now what I'm going to do is I'm going to create a random number. So I'm going to say random r is equal to new random. Remember last year we have I shown you random yet this year? Okay, but we dealt with random numbers last semester. So in Java, there exists a class called random. You can tell it's probably a class because it has a capital R, capital name. All right, and if I hover over this, it's telling me it wants to import java.util.random. So we'll import that up here. That's where that function lives. It lives inside of random. I think, didn't we have to import random last year for it in Python? Same thing. Okay. Java has actually a couple of random number generators. This is just the one I typically use. This allows us to get big numbers. Okay. So what I'm going to do is I'm going to create my fraction here, my first one, and we're going to say I'm going to say, let's see, math.abs r.next long, and then math.abs r.next long. I'll kick this down a line so we can read it a little bit better. And I'll do the same thing for this other one. All right, so showing you a couple of new things here. We have a math library that has a bunch of functions inside of it. One is called ABS for absolute value. So I'm saying, give me a random long. So this will give me a number in the range of negative 9.2 quintillion to positive 9.2 quintillion. It might be quadrillion, I don't know, but big number, negative 9.2 big number to positive, well, negative 9.2 super small number to positive 9.2 really big number. Got it? But I'm not guaranteed that this is a positive number. So I'll take the absolute value of that. Okay? So I'm going to build a new fraction out of a random numerator and a random denominator. I'm going to build another fraction out of a random numerator and a random denominator. I'm going to add those two guys together, giving myself a new number, which should be something, well, luck of the draw should suggest this should be something scary looking. All right. Oh, why did I get a negative number there? It was too big for long. Okay, so what we need to do here, it added the two together and it actually got a value. Well, when it multiplied the numerator and denominator, it got a value that was actually too big to fit inside of a long. Let's just give it a range. So I'm going to say r.next long. So I'm going to cheat this. I'm going to take the absolute value out. I'm going to say r.next long, and I think there's a version that lets me give it a range. 0 to does it not let me? Doesn't. Oh, next int has a range one. Ay ay ay. I'm going to go back to this just to prove my point here. And then I'll show you a better way of doing this. So I'm going to say divided by 2 for no good reason. I'm just hoping to massage it in there. All right, we got positive numbers. All right, so if a big numerator and a big denominator, But now I say reduce that. Well, how do we reduce a fraction? Well, we have to find the biggest number that evenly divides both the numerator and the denominator, right? So the biggest number that's possible is going to be the smaller of these two, right? It's going to be the smaller of those two numbers. Now, if we did, what was our previous thing? Was it 3/6 or something like that? 6/8. That would be, we start with 6 because 6 is smaller than 8. And we would say, does 6 divide both of them? It does not. Does 5 divide both of them? It does not. Does 4 divide both of them? It does not. Does 3 divide both of them? It does not. Does 2 divide both of them? It does. 3/4, we're done. So we started at the top number, or we started at the smaller of the two numbers, and counted down from there, checking if it evenly divided both. As soon as we ran into one, it just worked, right? So we're going to go into fraction. We're going to create a function here, public void, ninja, public void reduce. So we're going to add the ability for a fraction to reduce itself. That's why we don't need to give it parameters. So we're going to say, Mike, reduce yourself. So I'm going to think about my numerator and my denominator, and I'm going to figure out the greatest common divisor of both of them, ultimately giving myself a, more slim-fitting fraction. Oh, was that a fat joke?
Nope.
Go ahead.
So that would you do that by like having an if command that has like if the percentile division sign equals 0 and of one number and then the other, that would get you what you
Yeah, you're on the right track. Yep. So first I'm going to find out what the smallest number is. So I'm going to say long smallest. I'm just going to take a guess and say this dot numerator. Then I'll say that if this dot denominator is less than smallest, then I'll say smallest is actually equal to this dot denominator. So I'm going to say, oh, the smallest number must be the numerator. Then I'll ask a question to see if I'm wrong. Was the denominator actually smaller? If it was, I'll switch smallest to denominator. Once we get to this line here, smallest is the smaller of the two numbers. That's what we have at that point. Everybody good with that? So now what I want to do is I want to start at smallest and count down to 1. Because I know 1 will evenly divide both of them, right? So I'm going to say, while smallest is greater than or equal to 1, I'll ask a question. If this dot numerator, when divided by smallest, is equal to 0, and this dot denominator, when divided by smallest, has a remainder of 0. If both of those are true, then that means the current value of smallest evenly divides both of those values. So I'll say this dot numerator is equal to this dot numerator divided by smallest. This dot denominator is equal to this dot denominator divided by smallest. And then I'll say, my work is done. Right? And how do I make a function end? We talked about this a couple classes ago. Return. Now remember, this guy has a return type of void, which means I cannot return a value, but I can say, I want this method to end. That will kill the method off there. So once I find the number that evenly divides both, I will divide my numerator and denominator by that value, resetting the values, or changing the values, and then tell my function to die. Otherwise, if I have not found that value yet, I'll always say smallest is equal to smallest minus 1. Go ahead.
So will this just reduce it once? Like just once there's a number found that reduces it with remaining
Yes.
0? So it won't
Because we're going to find the largest value that will divide both of them. We're finding the greatest common divisor because we're starting at the smaller of our two numbers. We're counting down from there. Ultimately, we are asking, does the current value of that divide both of them evenly? As soon as we do that, we know we have found the largest value that divides both of them.
and that's why we can end it right away.
Correct. Yep.
So would it continue to try to find a number to divide it by if we didn't do return?
Yes, because it's going to always do this. We only execute this code if this Boolean expression is true. If we have found a number smallest that evenly divides both the numerator and the denominator. If we have found that value, then we're done. Fix our numerator and denominator, tell the function to die. If that didn't work, we're still alive here. If it makes you feel better, we can put an else in here. It's not going to hurt anything. So we can say otherwise, just reduce smallest so the next time through, we can check the next value. That make sense? You have a question?
Could you run this, see how long it takes?
I'm going to, but I'm going to run it on a small number first. Okay, so now we have a reduce, correct? So I'm going to go ahead and create a fraction test is equal to a new fraction 6 and 8. And we'll say test.display. Then I'll say test.reduce. Then I'll say test.display. So I should show a 6/8. Then I'm going to reduce it. And there's my 3/4. Ran pretty fast. All right. But now we're going to say answer.display, answer.reduce, answer.display, where answer is our crazy fraction.
Yeah.
Oh, we didn't luck out there. There we go. Remember, I was kind of forcing a big number. It got too big for the addition. That's why it went to negative.
Oh, good. There it goes.
So it's a reduced fraction.
It's not reduced yet. No, it's cooking.
Oh.
Yeah, it's currently reducing.
Oh.
Yeah. Yes, we're not done yet. This is just the initial display. That's just this line right here.
Oh.
Yeah, we're in the oven. Yeah, we are currently reducing. I bet you we can come back next class and this won't be done. Not kidding. This is a known time complexity problem. We are trying to divide two ridiculously large numbers by each other. I'm not even going to count the number of digits. This one just looks smaller. So let's say this is the smaller. So we're starting with this one, saying, does this guy divide himself? And then does he also divide this guy? If not, subtract 1, try it again. If not, subtract 1, try it again. There's a lot of subtracting of ones in this scenario. Now we can say, oh, well, maybe we can make it a little bit more efficient by maybe doing the square root. Some math tricks we can throw in there that maybe cuts down the total number of things, but it's still going to be a ridiculous number of things. Huh? Okay. It's a lot. It's a lot. So this is gonna take a while. All right. So his machine is working. you because you're just doing the same thing I'm doing, right?
Yeah, it's
Yeah.
just like going like.
I'm not even
His
trying.
processor is doing a lot of math and not being very successful. That thing's gonna heat up. Keep it plugged in. All right. So we're all convinced. We're all convinced
Yeah.
that, well, first of all, we saw this work, right? So we're convinced that our algorithm works.
If your computer
It
slows,
just might not be efficient enough to give us answers in our lifetime. It'd probably give us an answer in our lifetime, but it's going to take a while to cook, is the punchline. So if we go back to our fraction here, what are we actually calculating here? We're saying find the greatest common denominator. Common. That's what we're trying to find in here. Once we get inside of this if, we have found the GCD. It is smallest, the current value of smallest. Then we divide the numerator by the GCD, we divide the denominator by the GCD, and we're done. So what's taking a very long time here is the finding of the greatest common divisor. Okay? So yeah, usually you would see this as divisor, but for us it's the greatest common denominator. But the solution is the greatest common denominator. We're looking for the greatest common divisor of the numerator and the denominator. The biggest value that divides both of them evenly. All right, does that make sense? Go ahead.
I'm a little confused as to why you added, why you put the 10 there. Doesn't it,
I have found and applied the GCD, so kill the method.
if that only tells you one possible GCD.
There is only one possible GCD.
That only tells you one possible CD. Because if it, because if there's places where if you took those 2 points
Mm-hmm.
and divided them by something that they were both divisible by, but not the greatest one, you would get an answer.
Right, but we're guaranteed that this is going to be the greatest one because we are starting at smallest, which is the larger, which is the smaller of our current numerator and denominator. So we're starting at the biggest possible value that it possibly could be.
I was taking it from the outside.
Yeah. So we're starting at the biggest possible value it could be, and as soon as we find one, we know that's the greatest one. Does that make sense? Okay, so for our homework, we're going to write a public void reduce Euclidean.
What the heck is that?
Well, that's not just self-explanatory.
Well, yeah, really.
Use the Euclidean algorithm to make reduce more efficient. So now if we just come in here and we do a Google search, Euclidean algorithm. Let me give you one that looks nice and easy to follow. Yeah. So down here, they've actually given you an implementation of it in, this is just pseudocode. They've even called it a language. So greatest common divisor takes an A and a B. As long as B is not equal to 0, sets T to B. It updates B. This is that percent symbol. This is modulus. And then sets A to T. does this. This is like Python, where it does this over and over and over again until b finally becomes 0, and then ultimately returns a. So for your homework, I'll give you the link to this guy. Read through the beginning of this Wikipedia. It kind of explains how the Euclidean algorithm works. I'm not going to test you over how it works, but it kind of explains the mathy side of it. And then write our new version of reduced Euclidean, where instead of using our smallest loop thing that we're using, you instead use something like this to figure out the greatest common divisor of the numerator and the denominator. Everybody paying attention to what I just did? The inputs for GCD will be the numerator and the denominator, and that will spit out the greatest common divisor of those two values. And then you can divide your numerator and your denominator by that greatest common divisor, giving you a reduced fraction, and you will find that it runs way faster. Make sense? All right, so I'll give you the current code in reduce, and I encourage you to keep the current version, but comment it out when you go to test it. That way your program will finish. Okay? But then you'll see, so once you convince yourself it runs for a while, then you can go and test it with your GCD version, and you'll see that it runs almost instantaneously. Sound good? All right, so what are we practicing on this homework? We're practicing this idea of, hey, I've given you a math function that we know does something interesting. Convert that now into code. In fact, this Wikipedia even gives you the pseudo code of it. So you're translating that into Java. But read about this first so you kind of understand what you're doing. But effectively what we get here is a math trick for getting greatest common divisor. Homework shouldn't take that long. But what you'll see is in the end, you have a significantly faster function that does something we just tried to do, that we were kind of tricked into thinking it was going to be really, really fast because of the nature of it being simple math. Make sense? Good.
Just a random question. If we were to like write the long way in like C, for example, would it actually show an answer? Or would it still be like insanely long?
Same, just as long. Just as long, yeah. This is not a Java issue. This is a time complexity for the math issue.
Okay.
Maybe C would run 15, 20 seconds faster.
Really?
Yeah, I mean, this is simple math. This is not like a heavy lifting for the virtual machine.